energy scale, the magnetic energy in the ring also coming into play. And this is, I introduced that already, this is the Josephson coupling energy divided by beta L. So you can write this as 1 over 2 pi times finite square over 2L. Now you can compare KBT with this magnetic energy. So you can state fluctuations become important when KBT over EM becomes small. And if you plug in this definition, you find that this is nothing else than your noise parameter gamma times beta L. So now, and you can also write this as the ratio of the inductance divided by a thermal inductance, as we did for this condition here, where we write gamma as the thermal noise current divided by I naught. So if this ratio approaches 1, you have also you have strong thermal fluctuations. So if you want to operate in the regime of small thermal fluctuations, not only your gamma has to be small, I gave you already these values for the 2 different temperatures for the thermal current, but also the product gamma times beta L has to be small. And that means with the definition of this thermal inductance, the inductance has to be much, much smaller than this thermal inductance, which now scales with 1 over T. So at 4 Kelvin, your inductance should be well below about 6 picohenry. However, at 77 Kelvin, it should be well below a few hundred picohenry. And that made a big problem when people started trying to make sensitive high TC squids operating at liquid nitrogen. That was in the beginning not so clear, because typical squid inductance for squids operating at 4K are in the range of a few hundred picohenries. But if you do this at 77K, thermal fluctuations destroy, let's say, your flux states again. So you have to be aware, you have to consider both conditions to stay in the regime of small thermal fluctuations. Okay. To do this in a more quantitative way, you can do this doing numerical simulation, solving this coupled Le type equations, where you also plug in finite temperature, also using the RCSJ model. Again, most common expressions have been already derived by Claudia Tesche and John Clark in this paper published in 1977. What they find is that the transfer function, let's say in the limit of small thermal fluctuations, typically scales as 1 over 1 plus beta L. And they found that an optimum noise performance you get at beta L equals 1, not at very small beta L where you get the strongest modulation, but at an intermediate value. So this is kind of a design rule. If you want to make a sensitive squid, you should set your beta L to a value close to 1. And they came up with expressions for squids with beta L close to 1 and gamma about 1 over 20. So also the product gamma times beta L is about 1 over 20. So there you are still in the regime of small thermal fluctuations. So they showed that the transfer function scales with R over L, or with this condition, plugging in this condition, simply shows the transfer function scales with this characteristic voltage I naught R. And this is a quantity which kind of tells you how good your Josephson junctions is helpful for making a sensitive squid. So if you want to make a sensitive squid, you should look for junctions which give you a high I naught R product. That's very helpful. And then by doing numerical simulations, they found expressions for the spectral density of voltage noise. So this scales with KBT times R. For the flux noise, this scales with KBT L squared over R, or also for this energy in a resolution, which scales with KBT times L over R, or KBT divided by I naught R. Plugging in some number for this constants, basically for KBT, you find, let's take here the RMS flux noise, you get a prefactor of about 0.7 microfarad per square root hertz, times the square root of temperature in Kelvin, resistance in ohm, and inductance in hundred of picohenry, which is of the order for typical devices of unity, which tells you from the simulations typical RMS flux noise of well-designed squids are of the order of a microfarad per square root hertz. So basically what this RMS flux noise tells you is that in a bandwidth of 1 hertz, this is roughly the amplitude of your fluctuating flux you can detect. So that means you can detect changes of a millionth of a flux quantum on applied flux. So squids are in fact the most sensitive detectors for detecting changes of magnetic flux. Okay. Yeah, this was extended later on at the time. When we wrote this article for the squid theory. Also together with John Clark, and simulations have been done mostly by Reinhold Leiner. Let's say extending this kind of canonical expressions derived by Tesher and Clark from the regime of small thermal fluctuations to a broader range, also covering the regime of large fluctuations. Basically, the result was, in a nutshell, that you can factorize all the expressions, the transfer function, voltage noise, flux noise, energy resolution, into two expressions. One function just depends on beta L, and one depends on the product gamma times beta L. And just looking at the main graphs of this four panels, plotting these quantities versus gamma times beta L, what you find above, let's say about a value of 0.3, you start to lose a lot in transfer function. You start to increase a lot in flux noise, and also your energy resolution gets worse if you are in the regime of large thermal fluctuations. Yeah. Okay, yeah, that's the message. Good. Maybe a few words on Squid Readout. So I showed this graph already. So your squid is a flux detector. So you apply a small signal and you measure a voltage signal. However, this is not very convenient to read out. Ideally, you would like to linearize this periodic characteristics, or in other words, you always want to stay at the optimum working point. And there are a variety of readout techniques, and if you are interested more in learning about that, I can recommend Chapter 4 in the Squid Handbook, Volume 1, where all these techniques are described. Let me just point out this very basic concept of the so-called flux loop. So what this does, you measure, you are at some bias point, you measure a signal, which means you get a voltage change. This voltage change is compared to your bias voltage, where you want to operate the squid, is then amplified, integrated, and then fed back via a feedback resistor and a feedback coil with some mutual inductance to the squid. So any deviation from your working point produces a feedback flux, which compensates your applied flux. And then what you measure is basically the current which you need to compensate this applied flux by detecting voltage across this feedback resistor. And this way you get a very convenient way of measuring the applied flux simply as this amplified voltage, and you always stay at the optimum working point. And this kind of feedback electronics, this works with bandwidths up to several megahertz, I would say. I mean, intrinsically the squid is very fast, but if you want to operate in a flux loop in FLL, you are basically restricted to about 10 megahertz bandwidth. Okay. Let me skip that. There are some more advanced readout schemes. In particular, maybe I should make that point. If you have a very sensitive squid and you want to know what is the, let's say, the intrinsic noise of the squid, I mean, you want to measure the fluctuations, the voltage fluctuations across the squid, you have to be careful that you are not dominated by the preamp noise. And this, so the preamp noise should be always larger than the intrinsic flux noise times the transfer function. So it depends whether you fulfill this condition, depends on how sensitive is your squid and how large is your transfer function. And there are different schemes if you have a problem here, how to get around that problem, like this additional positive feedback or some AC flux modulation, also combined with reversing the DC bias current, which is shown in the next graph. But I think this will be far too much detail. I will not bother you with that. So it's just maybe the message is there are advanced techniques and there are commercial readout electronics you can buy if you want to use them. And this, maybe I make that point, this bias reversal helps you a lot by suppressing contribution of 1 over F noise due to IC fluctuations. So this is a spectrum measured with static bias, and this is with DC bias. This is a high TC YBCO squid which often suffers from high critical current fluctuations, and you get rid of this 1/f noise if you do this bias reversal. Okay, these are just some examples for some squid structures. It's very simple layouts. In principle, if you want to do some measurements, you always rely on the fact that you measure changes of fluxes, but you can think of different types of input signals you want to detect, delta X. And via some appropriate input circuit, you convert this into a flux change, and then you have the readout electronics to, at the end, measure a voltage change. The typical input signal would be an applied magnetic field. This gives you a magnetic flux signal, which is delta B times the effective sensing area of your device. Or the effective the inverse of the sensing area is the so-called flux to field conversion factor, which tells you how much field B naught do you have to apply to induce one flux quantum in the squid. And that's, by the way, also the way how you measure the effective field in experiment. You trace out your voltage versus field modulation, and you look how much field you need for changing the for inducing one period, and this tells you your field to flux to field conversion factor or the effective area. And this you need to know in order to translate from flux sensitivity to field sensitivity. So the magnetic field resolution, I quote here the RMS spectral density of field noise, is the flux noise divided by the effective area. So for a sensitive squid, you want to have low flux noise. At the same time, you would like to have a large sensor area. And that's somehow a contradiction, because low flux noise you get easily by making your squid very small, having very small inductance. But then it becomes very small to couple signal into the squid. And there are some solutions to that, some properly designed layouts in input circuit structures which have been developed mainly by Mark Ketchen at IBM in the 80s, where you start with such a kind of washer structure where you can easily calculate the effective area, which is just the size of the inner hole times the outer size of your washer. In practice, you have to cut a slit into the washer and place a junction somewhere to have a DC squid. And for plugging in some numbers, so typical washer sizes, let's say 0.5 millimeter, your hole is maybe 20 microns. You can calculate the effective area of 100 micron square, flux to field conversion factor of fraction of a microtesla per phi naught. And if you plug in typical value of flux noise, 5 microphi naught per root hertz, with this effective area, that tells you you can build from just a single squid field sensor with a sensitivity of 1 picotesla per square root hertz. So in bandwidth of 1 hertz, you can detect a millionth of the Earth magnetic field in field change.
Don't you have problems with vortex in that design?
If you do it properly shield, yes. Yeah.
Because it's very large. So
Yeah. So typically for applications, these squids are then shielded, to get rid of vortex. But okay, this value is nice, but it's not great. And you can do much better, and this was developed by Mark Ketchen. If you develop, John Clark termed this as a hearing aid for squids, you develop this closed superconducting loop, which is a flux transformer. So you have a big pickup loop which connects all the field you want to detect, connected in series to an input coil coupled by a mutual inductance to the squid. And now if you apply a magnetic field, it induces a screening current IS, which is just the flux, B times the loop area divided by the total inductance, LP plus LI, and this flows through the input coil, which can be a multi-tone input coil, to efficiently couple flux into the squid. So the flux coupled into the squid is just the mutual inductance times this induced screening current. And this mutual inductance is defined by a coupling factor alpha, which can be maximum 1 times the square root of these two inductances, squid inductance, input coil inductance. And then you can simply calculate the effective area, what is phi A divided by B, by plugging in these equations. You get this expression, then you can show that you can maximize the effective area by properly adjusting the input coil inductance here. You can make a so-called match transformer. You choose the number of windings here that the input coil inductance matches the pickup loop inductance of this large loop. This gives you some simplified expression here. And this input coil inductance is for strong coupling is just given by the square of the number of terms times the squid inductance. So this at the end gives you expression for the effective area, which can now be significantly enhanced. For putting in some numbers, you get now of the order of some millimeter square instead of 100 micron square. And so this is just a schematic how this then looks like. So essentially you make this washer type squid because you want to place a multi-turn input coil on top of that. And this input coil is then connected to this pickup loop. And such devices come up with a field resolution of about a femtotesla per square root hertz. And this is then very interesting for many different types of applications. There's another scheme which is so-called multi-loop squid. I will not discuss it here, just show it because I like the picture a lot. It's beautiful design. Okay, and a femtotesla, this is a factor of 60 billions below the Earth's magnetic field. So the ratio is just the ratio of the thickness of a sheet of paper to the radius of the Earth. So it's a really impressive sensitivity, and in any case, if you really want to use this very high sensitivity, you have to operate in very well shielded environment.